not everything is capable of being integrated. So there's some functions that are just too difficult to do. So we have to use approximations. Now, we started off by looking at rectangles and they went great. We've got another shape, that being the trapezium, which actually cuts that overestimate or underestimate, depending on the concavity of the curve, down very quickly. So if I want to find this area between A and B, see if I draw the trapezium, then there's a whole triangle there we're not including in that overestimate. A trapezium is a much better shape here. It will get us a better estimate. So a reminder of finding the area of a trapezium. Height over 2, well the height for our one would be B minus A. And then the sum of the parallel sides. Well the parallel sides would be function A and function B. But just like we saw when we were looking at rectangles, the more rectangles we had, the better the approximation. Well, the same deal here. The more trapeziums we have, the better the approximation. Let's split it up into 2 trapeziums. So I'll put C in the middle there. If I was to add these two together, but I can factorise. Because I place C in the middle, C minus A would be the same as B minus C. So I could factorise, and well, I wrote it as C minus A. I could have just as easily have written it as B minus C. But what we'll end up with is, function A twice function C, because it's involved in both of the trapeziums. So we'll have twice function C and function B as well. Okay, well let's split it into 3 trapeziums. And again, I'll make sure they're all equally spaced. Add them all together. But C minus A would be the same as D minus C, would be the same as B minus D. So I could factorise it again. All the ones in the middle are involved in 2 trapeziums. So we'll get twice those function values. So it'll always be 1 times the function values at the end and 2 times all the ones in the middle. That allows me to come up with a formula. Yes, the exact amount would be the integral if we could work it out. If we can't, we could do an approximation. H on 2, so whatever the height of the trapezium ends up being, C minus A, D minus C, B minus D, whatever, over 2. The inside we'll have, well I've called it y naught for the function value at the start and yn for the function value at the end, and then I've just said, well, 2 times the others, all the ones in the middle. Now why did I start at naught? Well, that's because the number of trapeziums will be n, but we will always end up with 1 more function value, because each trapezium has a function value on either side. So you'll end up with 1 more function value than you do the number of trapeziums. So I start at naught, so I end up at n. It doesn't really matter. Some people start at 1 and end at n plus 1. Either way. Let's do an example. Now I've deliberately picked a function here which we know its exact value, because if you look at it, what we've got there, 4 minus x squared to the power of a half, or the square root of 4 minus x squared, it's a semicircle. Well, actually it's a quarter of a circle, isn't it? Because I'm going from 0 to 2. So I do know the exact amount for this, but let's see how good our trapezoidal rule is. We're going to use 4 intervals. Sometimes they use the word intervals, sometimes they'll say trapeziums, sometimes they say sub-intervals, sometimes they say strips. How many are you breaking it into? We're going to have 4. Work out the height. Well, it'll be B minus A, so the 2 endpoints, divided by the number of strips, trapeziums, intervals, whatever they've called them. 2 minus 0 and 4, which is a half. I then draw up a table of values. And I'll mark off every half for the x values, substitute in. Now they've said to do it to 3 decimal places. In my table of values, I usually carry it to 1 more, in case there's a rounding error later on. So if I've got 1 more, I should be okay. There's my formula, h on 2, y naught, yn, 2 times all the other ones. What I do though is, to remind myself on my table of values, I write 1 on the top of the n ones, and then 2 on the top to remind myself, okay, I'm going to multiply the n ones times 1 and the middle ones times 2. So it just reminds me I've got to do that. Sub in. So a half on 2, and there we have it. So 2 and naught, they're the end ones, then 2 times all the ones in the middle. We end up with 2.996. That exact value would be pi. Okay, we've got a circle of radius 2, so the whole circle would be pi r squared. For pi, we got a quarter of the circle. How good's my approximation? There's my percentage error. Yeah, it's 4.6% error with that one. There is an alternative setting out that I saw once, which I thought, not too bad, so let me show it to you. Right, there's the table of values. So same question. There's the table of values. There's the answer. Now have a look at what we've constructed there. On the top of the fraction is exactly the same thing that I put in the middle of the parentheses. So the n1's twice all the ones in the middle. On the bottom of the fraction, I simply write all of those numbers, the ones I put in the box there. 1 plus 2 plus 2 plus 2 plus 1. In other words, what the function values are being multiplied, each of them. And then I multiply it by the overall width of what we're finding the integral or the area of. And we were going from 2 to 0, so that's 2 minus 0. And if you do your calculation, yes, that does come out to be the answer we're looking for. Not a bad little way of setting it out. Okay, here's an HSC question from 2020. Kenzo's driving a car along the road. Friend records the velocity of the car in kilometres per hour every minute over a 5-minute period. Table velocity in hours, but for some reason, well, maybe because of the decimals, rather than saying 1 minute, 2 minutes, they've gone 1/60th of an hour, 2/60th of an hour, 3/60. Anyway, that's the table of values we've been given, and the velocity for all of those. They've then told us that, hey, if we could work it out, the distance would be this particular integral. So you integrated the velocity going from 0 to 5 on 60, if we could work it out. Now, clearly we can't work that out. We don't have an equation for velocity. They had said, well, use the trapezoidal rule and those velocities to work it out. So in other words, we're approximating this integral with the trapezoidal rule. Okay. Well, there's the table of values. There's my formula. I know I'm going to go 1 times the n1's, 2 times all the ones in the middle. H on 2, well, the height of each one is 1/60th according to our table of values there. And then inside those braces, I've got 60 and 67, and then twice all the ones in the middle. And to 1 decimal place, 5.4 kilometres is the answer. If I was to use the alternative setting, well, then that's how I would do it. On the top of the fraction, what was inside those braces? The 60, the 87, 2 times 1's in the middle. Bottom of the fraction, all of those things I multiplied the function values by. So 1 plus 2 plus 2 plus 2 plus 2 plus 1, and multiply by the width of what we're doing. And it was 5 over 60 minus 0. And yes, that does come out to be 5.4 kilometres. Okay. So that is our approximation method known as the trapezoidal rule.